Right, getting into chapter 3 lesson. So this is the first section as well as the first part of section 2. So this begins with just some basic probability stuff, and this is just reminders. You all know what probability is and how this works, but it's simply the number of events that you're looking for out of the total possible. So we refer to that total possible as the universe or the sample space. Hopefully you watched my Venn diagram video that I posted on the website yesterday, is there's a great connection to the use of Venn diagrams with probability. So here we go, just a couple basics, and this is really just for the noting of vocab on something like this. But if you had these letters on tiles within a bag and we said what's the probability of reaching in and pulling out a vowel, well, we'd say, we'd look at the sample space and we say, well, this is the sample space. This is everything I have to choose from. So we see this as our total possible to choose from, and that's what ends up down here. This is the vowels. This is the probability of the event that we're actually looking to happen, which is getting a vowel. So we'd say, well, these are the vowels that are in there, and there are 3 of those. And so that's where we're going to come up with the top number of this. And so we're just showing that with these numbers here. But this is the number of ways of getting what we want out of the total possible. As we go through, you can write answers as fractions, decimals, in the form of a decimal or a percent. And so there's just one of those things where, check the directions. If the directions don't say otherwise, put the one that would make sense. There's no sense in turning this into a decimal from here. It just makes sense to leave it as a fraction. Your popular questions for these are rolling 2 dice. So there's a great diagram that would look like this. We call this a lattice diagram. Anytime you roll 2 dice, this is just a great way of exposing all 36 outcomes within a simple grid. And then you can go in and just kind of highlight the ones that would make sense for the problem that you're dealing with. So we're going to see this as the first die, and this would be the other die. So these are all the 36 possible outcomes that you could get when you toss 2 6-sided dice. So if we just said, what's the probability that you get a sum of 6? Well, if you go in and just so you can see the circles represent the sums of 6. So right here, like that would be a 5 and a 1. Of course, those add up to 6. A 4 and a 2, 3 and a 3, 2, 4, and 1, 5. And so those are the 5 cases out of the 36 that could have a sum of 6. If we said a sum greater than 9, well, right here you're seeing all the sums greater than 9. So it starts with the 6, 4, right? Obviously that adds up to 10, so that's greater than 9. So right here you're getting your sums of 10. These are your sums of 11, and then you have a sum of 12. So those 6 out of 36 represent your sums greater than 9. If you ever have a fraction, you should always reduce your fractions before moving on. So right here we have a less than 6 or greater than 9. One thing to make note of as we move through this chapter is there are a lot of formulas in your formula packet for this chapter. All of these that you see here all connect to probability. So this is the one we started these notes with. We're going to be looking at complement events, all these. So right now we're looking at this case right here, right? So it said an or case. So if you see the U symbol, that represents the word or. So this is the probability of A or B happening. And we simply would add those 2 events together that you're seeing right here. So let me go back to the notes. Whoops. So in this case, if we said less than 6 or greater than 9, I'm just going to add those cases together. So cases less than 6 are the triangles that you're seeing right here, right? And so you have 10 of those, so 10 out of 36 plus the 6 cases that are greater than 9. So if we just add those scenarios together, this is our probability. This next part just explains the difference between theoretical probability and experimental probability. Theoretical probability is what we're most familiar with. It's in theory what would happen if we did something. So in this case, if we were to toss 2 6-sided die, let's just say we were going to throw them 36 times, we would say, well, how many times would we expect to get sums of 6? Based on the probability, we would expect that to happen 5 out of the 36 times. But we don't know for sure that that's what would actually happen. That's just the theoretical probability. Experimental probability is when you actually perform the event, what really happens in your specific case. And obviously this could change from one experiment to the next. If I conducted this experiment 200 times and I got these outcomes, so I got 32 ones, 33 twos, so on and so on. If these were my outcomes, well, if you were to perform the same experiment and do this 200 times, yours would certainly most likely be different than mine. And so these are just results based on an experiment that was conducted. Notice this is not playing out exactly the way you would expect them to play out. Based on theoretical probability, I would get the same number of ones as I would twos, as threes, fours, fives, and sixes. These would be equal values, that based on theoretical probability. So if we say what's the experimental probability of tossing a die and showing a 3, well, that happened 30 times out of the 200, so this is the experimental probability. Theoretical probability of tossing a 3 is 1 out of 6. And so you can see this is slightly different than the experiment that we conducted. So if we have a certain probability and we're going to do something a certain number of times, we would say, well, what's the expected number of outcomes that we think we'll get? So it's simply the number of times that you're going to do the event times the probability of getting what you want. This formula is also in your formula packet. You would find it right here. So that's your expected number probability. We do link that with statistics and the mean value, but that is also the expected outcomes that we get for probability. So if we said, we were to do something 600 times, the probability of getting a 3, well, we're doing it 600 times. The probability of getting a 3 is 1 out of 6. So if we multiply those, we would say I should get a 6 100 out of the 600 times, based on the theory. Well, what happened in this experiment, right? This was the probability of getting a 3 times the 600 events. We would expect that to happen 90 times. Complement events, a really simple concept. A complement event is just the opposite of what you want. So if we said, what's the probability of a certain event happening? The complement event would be the probability of it not happening. And you can see those should always add up to 1. Just logically, that should make sense. If I take the number of ways of getting what I want plus everything else, or the opposite of getting what I want, those create the total sample space. I'm either getting what I want or I'm not. There is no other option. So that should represent 100% of the options. So a real simple use of that, and this is also in your formula packet, but a simple use of that would simply be this. The probability of some event happening is 29%. So the probability of it not happening would just be the remaining 71%. So I would just do 1 minus event A in order to get not A. Getting into this part, and again, this was all explained in the Venn diagram video that I already posted for yesterday, but again, you can see Venn diagrams are just a great way of organizing your information in order to set up some probabilities. So for this one here, we're looking at a standard 52 deck of cards. If we were to take just simply one card out of the deck, and we said, what's the probability that it's a face card and it's red? Well, if you look at the Venn diagrams, a face card is a jack, queen, or king. There's 4 jacks, 4 queens, and 4 kings. So there are 12 face cards in a deck. So these represent all 12 face cards, is this circle right here for F. This circle represents all 26 red cards. In a deck of cards, there's 52 cards. Half of those are red, half of those are black. So there are 26 red cards in the deck. Notice the area of overlap. There are 6 cards that are both a face card and red. And so now, based on just the organization of this Venn diagram, it becomes really easy to do a probability. So if we said the probability that it's both a face card and a red card, well, I look at the diagram and say, well, there are 6 of those out of the 52 cards in the deck. And so that's the probability that we can set up. Notice the word and the word or. Big differences between those. This one in particular said, what's the probability of getting a face card or a red card? And so this is something we could do with a Venn diagram or a formula. So I'm going to show you both, just so you know how to use both. But Again, here are the numbers laid out for the Venn diagram. Notice these 20 cards, right? These are the 20 cards that are not a face card or red, and that's where that 20 came from. But if we said probability of getting a face or a red card, well, we look at this and say, well, this is my or scenarios right here. These are all the cards that are either a face or a red card. And so I could just add those up, put it out of 52, and that's one way of getting my answer. So these represent the 32 cards that are either a face card or a red card. And that's a great use of Venn diagrams. Here's the way you could have done this with a formula that is in your formula packet. So if you look at the formula packet for a minute, so look at this one right here. Remember, this is your or symbol. So if we said, what's the probability of a face or a red card? Well, if I add those two together, notice there's an extra piece on this. And I'll talk about that in a minute, but this would be the probability of a face card, which is 12 out of 52, plus the probability of a red, which is 26 out of 52, minus whatever they have in common, or minus the probability that it is both face and red. And there are 6 of those. So if I was going to use the formula, I would say, well, there's 12 out of 52 face cards, 26 out of 52 red cards, minus 6 out of 52 that are both face and red. And so we're subtracting those out. Otherwise, you would be counting those twice here and here. And so we're subtracting out what they have in common, or the overlap between the two events. Moving on, so if we said, what's the probability that it's not a red face card? So remember what we found up above, right here. The probability that it's a red face card is 6 out of 52. So if we said that not a red face card, we just do 1 minus 6 out of 52, and these are the remaining cards that are not red face cards. So that's just simple use of complements. Probability that it's a red face card or a black card. Notice this one. Here's an or case. But if I said a red face card or a black card, look at those two events. Could you ever get a card that is both a red face card and a black card at the same time? That would not make sense. So if you look at the formulas, this is what you call mutually exclusive events. There's no overlap. There's nothing they have in common. I cannot get a card that is both a red face card and a black card at the same time. That wouldn't make sense. So we leave this part out because these events are mutually exclusive. There is no overlap. They have nothing in common. So we would say, well, what's the probability of a red face card plus the probability of a black card, and we just add those two events together. So that's what you're seeing on this one, is we're saying probability of a red face card, we already figured out up above, that's 6 out of 52. All right, that was these guys, 6 out of 52, red face cards, plus the probability of getting a black card, which is 26 out of 52, and so that's where we get this answer. Last one, probability that it's not a red face card nor a black card, that would just simply be the complement of this. So if we said getting a red or a black, well, this would just be the opposite. This is not getting a red or a black, and so if I just do 1 minus this probability, then I get its complement, which would be the other 20 out of 52 cards.